Hi, I'm Danilo. I'm part of the developer relations team in AWS, and today we have Pete that is going to talk with us about genomics. So, Pete, can you introduce yourself and what Genomics England does?
Sure. My name is Pete Sinden. I'm the Chief Information Officer for Genomics England. Genomics England was formed by the UK's Department of Health to see how we can understand people's individual uniqueness to target precision medicine and personalised healthcare.
That's really a fascinating field. So, what scale of data do you process to do that?
So we currently hold around 60 petabytes of data, and we expect that to grow to maybe 300 petabytes over the next 5 years. Each individual person's genome is roughly 200 to 300 gigabytes, but with some of the newer technologies, it could be as much as a terabyte for one person.
So who are your users? Who is using your platform?
So we have two main services. There's the service to the UK's National Health Service. So that is where, as a patient, I can come in, I have a rare disease or I have cancer. I don't understand why I have this rare disease or what's causing it. And through working with my doctor, I can get a result that's powered by the bioinformatics that we deliver through Genomics England. If I'm a researcher, that's another type of user. I have controlled access to the 150,000 genomes that we currently hold to advance science and find new therapeutics and new diagnostics that can be fed back into the clinical side. So we call it the infinity loop, where as the number of participants grows, the number of people who get a diagnosis and consent to research, the research pool grows, which means researchers can learn more, which feeds back into the community, which means that more people can get a diagnosis. So it's a virtuous infinity loop.
And to process this large amount of data, how do you scale computing?
So computing, it's probably worth saying where we were. So we were in a larger data center. Everything was stood up always on VMs. It was quite costly for all the time they weren't being used because actually the workloads are very lumpy. In moving to AWS, we've re-architected. So we didn't just migrate, we re-architected as we migrated. So we containerized a lot of our services where possible. We took the chance to optimize around a lot of other areas as we were going. We use components such as Fargate for containerized services. Where possible, we've used Lambda functions to trigger event queues and make that much more efficient so things aren't sitting up and waiting. And through that, we can basically scale horizontally through rolling out additional containers, spinning up more containers with the same things, processing data more effectively in parallel.
And so you mentioned that you use AWS Lambda. Now I'm really interested in serverless technologies. How do you use Lambda in this architecture?
So we use Lambda to create relatively small functions, which largely trigger events and trigger different pieces of processing. So we've got bits of Python code that are called at the right times. The time it takes from someone to order a genomic test to getting the answer back is several days. And there are lots of different event points through that with multiple organizations, from the originating clinician through to the plater who puts the blood into the tubes the right way, to the sequencer who then takes that, the extracted DNA and sequences it to give us back loads of letters in a flat file. And each point there's a delay. Now historically we would daily batch collect things and nightly run things, and that adds effectively a 24-hour lag into the process. We don't need to do that now. Anytime an individual's results appear anywhere in the chain, it triggers the next function in the chain, stands up the services needed, well, it's in a serverless fashion, and rolls on to the next piece. So we have much less batch and wait, and the cost optimization is really good. So a service that was costing us something like £60,000 a month is now forecast to cost us $1,200 a year. And
you also mentioned Fargate. Why did you choose AWS Fargate to process to manage your containers?
So we wanted to minimize the amount of under the hood work that we had to do. It's a really good self-contained service. We don't have to worry about the underlying infrastructure. We don't have to worry about all that Ubuntu patching that we used to do in the past. It scales out really well. All we have to do is drop a Docker containers in there and off we go. So it's a great service.
You're processing really important data sets with this architecture. So what about security and how do you manage data protection?
So data protection is really important to us. We have very tight controls on data being retained within the environment. So researchers can't take data out of our environments and process it elsewhere. They can bring other data in, so they can process their own data alongside. The data they bring in sits in their own workspace, so it's hidden from anybody else, but they can bring it in. And then we have an airlock control and a sort of formal committee to discuss and approve any results going out. So it's only derived results, the final answer to the question, that can leave the environment. In terms of the security around that, So moving to serverless gives us a big advantage than where we were historically, because we don't have to keep up with that patching routine. We obviously have to scan our containers with things like X-ray and understand what's going on inside them, but the underlying infrastructure is no longer a concern for us. And the rest is the ordinary security you'd expect around firewalls and WAF and Security Hub and Inspector and GuardDuty and Darktrace.
So all the security services to monitor and find if there's some finding or some incident going on. Okay. And what about what you're working next? Would you like to share some of the things that you're working next?
So we've got some really exciting things coming up, and I think the fact that we've moved to AWS will give us some real advantages, because some of them are more greenfield. So the migration we've just been through was taking something that was built before, that was built in a certain way for a certain time and was cutting edge. No one was doing this when we started. So obviously the technical debt that builds up over time is to be expected, but now we've got some greenfield pieces we can, and we transitioned a lot of the architecture through migration. We've got a real chance to go faster. So a couple of these things, the AI ML side of things is really important to us. So flipping the scientific model on its head somewhat, looking at pattern matching across multiple data sets to see if we can identify correlations that may be causal, and then looking for the causes rather than hypothesizing a cause and then trying to prove it true or false. So that's a really important shift. It's really important for cancer, where we can look at imaging data and many other data sources at the same time. We're also looking at a screening program for newborns. So this is at the time of birth, if the parents of a child would like their child to be sequenced to see if they have any potential rare disease, and if so, what do we do about that? Because we wouldn't screen for everything. It's not about keeping all the data. It's about screening for known conditions where there's a specific intervention that can happen in the first months or years of a child's life that would give them a much better life for the rest of for going forward. So there's lots of dietary treatments and those sorts of things that are really important. So newborn screening. And the other main thing is diverse data. So we want to make sure that the diversity of our data sets represents our population, so that everyone can benefit from personalized medicine and there's no specific communities that are either included or excluded.
That's great. So thank you, Pete, for finding the time to chat, and let's meet again when there's these next steps going on.
Thank you very much.